Good morning. Just as a reminder, when we start, if you could turn your cameras on, that'd be helpful, just to see your reactions. Last Thursday, from your faces towards the end of the lecture, I could tell that people were starting to lose it in terms of don't know what's happening. Maybe it's too much math for an hour and a half, probably. So I'll briefly go over some of those this morning before we move on, because the particle in a box is one of just a handful of solutions that we can actually solve the Schrodinger equation for. And it's typically the first one that people actually solve. So I want you to sort of understand sort of the steps in the processes and more how we think about solving the Schrodinger equation. All right, there's only a handful of us here. I wonder what's going on. I know a couple of people are on sports duties. All right, let me just adjust one tiny thing. All right, how's everybody doing? Thumbs up, thumbs down. Yeah, weather's getting nice and warm. Sun's shining this week. It's all good. It's all good. It's all uphill or downhill. Downhill sounds bad, but it's supposed to be the easy path. Anyway, spring's on the way. That's what matters, which means that we can actually be outdoors again and eat food at restaurants outdoors and all that cool stuff. Before I begin, does anybody have any questions for me in general or about anything? All right. So the Jupyter notebooks, the third Jupyter notebook is due this coming Sunday. So make sure you look at that. Whenever I make these, I try to predict what we'll cover over those 2 weeks. So I hope I didn't went too far ahead with them. I don't even remember what's in the third one at this point. But yeah, if you have any questions about those, let me know. It's actually easier for you to just set up a Zoom call with me to go over any problems, because it's difficult to describe what's happening via email. So if you're encountering any issues, just send me an email and we can set up a time to quickly look at things. All right, let's do some recap. And I like to do this at the beginning of every lecture just to sort of remind you of what we've done. And by now I've said the next statement about 1,000,000 times, but hopefully that means you know it by heart. But the very first postulate of quantum mechanics. So when we were setting up quantum mechanics, right, we said that we wanted to describe particles as waves. And so what we said is we needed to give the particle a wave function. We call that wave function psi. And in that very first postulate, we said that psi contains everything that we would ever need to know about the particle, right? So the magic is in this wave function psi. We went over a few rules about what psi can be, right? We said that it was continuous and single valued and all those good stuff, but I never actually told you what psi is. However, and I forgot what postulate number this was, might have been 5 or 4. We mentioned that to find psi, it must satisfy the time-dependent Schrodinger equation, this equation right here, right? So this is how we go about finding psi. Whatever psi is must satisfy this equation. But I also said that for stationary states, we could simplify this and just use the time-independent Schrodinger equation, which just looks like this, and it's much easier to solve. So that's how we go about finding psi. We solve, if it's a time-independent system where the energy doesn't change over time, we can just solve the time-independent Schrodinger equation. This is the time-dependent Schrodinger equation. So that's how we find psi. right? And so that's what we end up doing when we solve for the particle in the box. We solve for this equation for a very specific case. And we'll do that for a couple more specific cases throughout this course. All right, so that's our recap. And then we started looking at the actual particle in the box when we try to solve that equation. So particle in a box. And before I even started that, I drew you a picture, right, of, mountains maybe, and a little ball rolling between sort of the valleys of this mountain. And I want to stress the importance of sort of visualizing things in this way. The mountains, right? The hills, the mountains themselves represent potentials. Some people call this a potential surface, right? Because it's kind of like the surface of a mountain. It's sort of, it's sort of where your particle is going to live on. So it's the potential surface or potential energy of what we're looking at, right? The ball here is going to be our particle. And the height that you drop this ball from, right, is going to be the energy of the particle. So you can think of the y-axis as energy, right? And there are two types of energies here to consider: the potential energy of the sort of mountains and the height at which you drop the ball. That's the energy of the particle itself. So there's two types of energy. There are potential energy of the surface and the energy of the particle. And that image, I want you to always keep in your head of whenever we're talking about systems, if you can imagine what the potential surface looks like, right? Remember, all of our systems is made up of kinetic energy plus the potential energy. But kinetic energy is always the same. It's the potential energy that is different. So in each case, if you can imagine what the potential energy would look like, kind of like hills and mountains and valleys and stuff, you can actually get a very good picture of what particles are doing in that system. For example, I drew that the Coulombic potential, which is the potential between positive and negative charges, is something like this: charge 1 times charge 2 over stuff times r, right? So r is the distance between the two particles. So if we have the particles very close to each other, the potential is very negative, and as they separate, it gets positive. So that's the potential energy surface of two charged particles. So if you imagine a ball being dropped in here, it will sort of live in here, right? Similarly, if you imagine two charged particles, let's say a positive charge and a negative charge, right? Let's say the positive charge is fixed and the negative charge is moving. The negative charge would like move near this positive charge and wouldn't be able to escape necessarily. Similarly here, if you drop the ball in here, it would roll between this two parts of the surface, but wouldn't be able to escape because of the energy. That's a very classical picture. So that's why I wanted you to sort of be able to do this sort of imagining, if you will, every time you see potential surfaces and you see particles with energy. The particle in a box case, we simplify that and we just say that the mountains are infinitely tall, right? So the potential here is infinite. And in the valley, the potential was 0, right? So that's the setup that we had for the particle in the box. And then we had our little particle inside that box. And so what this means is the particle can never escape the box because the potential is infinite. Kind of like infinitely tall mountains, though doesn't matter how much energy you give that particle, it will stay inside that valley, right? So then what we did was we wrote the Schrodinger equation, which I mentioned was kinetic plus potential energy. That's for the Hamiltonian. So this is the Schrodinger equation, right? H psi is equal to E psi, the time independent version. And H, we said, was just kinetic energy plus potential energy. It's the total, H is the total energy, and that's the only two types of energy we work with. And but the potential energy, it's 0. It's infinite outside the well, but we don't really care about outside the well. We care about inside the well. So the potential energy was 0. So the Hamiltonian was just the kinetic energy, which we know is negative h bar squared over 2m. And for one dimensions, it's d squared dx squared, second differential with respect to x. So then this was the Schrodinger equation, right? Once we accounted for the fact that we had 0 potential, that was the Schrodinger equation. And what we needed to solve for was the wave function and the energy. And that's how you solve the wave function. You sort of set up your Hamiltonian, you set up your Schrodinger equation, and then you try to figure out what functions fit in this equation, right? What functions set up eigenvalue equations. Now, we talked about how all of these are constants, so we're only looking at the second differential, and we wanted to know when second differential of a function returns the same function. When does the second differential returns the same function? We came up with a few cases. There was sine kx, there was cosine kx, there was e to the ikx, where k is all constants in these situations, and e to the negative ikx. These are all functions that fit the bill, right? If you take the first differential of each of these, just differential of sine. So this is the first differential. Differential of sine is cosine. Differential of cosine is minus sine. Differential of e to the ikx is ik e to the ikx. And differential of e to the negative ikx is negative ik e to the negative ikx. And then in each of these cases, the second differential should give you back the original function. So here we end up with negative k squared sine kx. Here we end up with negative k squared cosine kx. Here we end up with negative k squared e to the ikx. And here we end up with negative k squared e to the negative ikx, I think. So in each of these cases, we end up with a constant times the same function again, same function, same function, same function. And all of the constants are real, not imaginary. So these are all possible solutions. And that's the process that you use whenever you're trying to solve the Schrodinger equation. It's kind of like looking and guessing and checking, kind of. If we were a math course, I'm sure there are rules to finding the various functions that fit this equation. In this course, I'm just telling you what the functions are. We don't have to rack our brain to come up with all the different possibilities. So then, if you want it to be as general as possible, we said that the psi can be written like this, right? Where a and b and k are some constants that we don't yet know. So this was the general solution. But that's not satisfactory because we still don't know what a, b, and k are. But if we look at our potential, we know a few things, right? So let me just erase some of these lines so that we can see what's going on behind the scenes. We know that for starters, if the potential is infinite outside of the box, then there's no wave outside the box. The wave should be flat, 0 outside the box, right? But remember when we talked about wave functions from all the way back before, we said that they should be continuous and all that good stuff, right? So if the wave is flat outside the box, then the wave inside the box can't look like that because it's not continuous. There's a discontinuity right there. Do we see? So to make the wave continuous, both from inside to outside the box, it means that the waves at the edges of the box must be 0. So then we can draw whatever wave we want inside the box. But the waves at the edge of the wave at the edges of the box must be 0 because the wave has to remain continuous. It can't be sort of disjointed. The wave outside is 0, the wave at the edge should be 0. And if we set our box to go from, let's say, let's use that color, x equals 0 at one end to x equals some length a. So that means that the length of this box is a, right? Then we know that when x is 0, the wave function should be 0. And when x is a, the wave function should be 0, right? Because we know it should go to 0 at the edges of the box. So we did that, right? At x equals 0, we know that the wave function goes to 0. So we have 0 is equal to a times cosine of kx plus b sine of kx. And we know that, so x is 0, right? So this is cosine of 0. This is sine of 0. Again, this is just recap. Sine of 0 is 0. And so for this part to be 0, and cosine of 0 is 1, right? So for this whole equation to be 0, a must be 0. So we learned that a is equal to 0. That's the first thing that we learned when we examined the left boundary. We then examined the right boundary. At x equals a, we know that psi should be 0 again, right? Because that's the right edge of the box. So we did that. So psi is equal to 0 at x equals a. So what we're left with is b sine of k times a. So b sine k times a is 0. So either b is 0, but that doesn't, if b is 0, then the whole equation is 0, and that doesn't make sense. So it means that sine of k times a is 0. And we talked about when is k times a sine of something 0, and it's when k should be equal to 0, 1, 2, 3, all integer numbers only. And then we further said that k can't be 0 again, because the whole equation will still be 0. So we learned that k, there are many different possibilities for k. They're all integers. So those were the two different boundary conditions. And then we examined the third thing. So let's do 1, 2, 3. The third thing that we did was normalize this wave function, right? We know that the integral of the wave function should be 1 when it's normalized. And by normalizing, we found that b is equal to square root of 2 over a. And so by so doing that, we found that this wave function, right, this function of x, should be, we had originally a times cosine kx plus b sine of kx. But we learned that a is 0, so this whole part was 0. We learned that b was the square root of 2 over a. And we learned that k, sorry, k was 1 over a, 2 over a, 3 over a, and so on. So this becomes sine of k times x. K was an integer over a, so we just rewrite this as...
Isn't it an integer times pi over
Yes.
a?
Forgot that. Thank you. It was n times pi x over a. This goes to 0 when the angle is pi or 2 pi or 3 pi or so on. I said 1, 2, 3, 4, but I meant pi, 2 pi, and so on. So yeah, this was the equation for the wave function that we come up with. It depends on what the length of the box is. And right, so that's A is the length of the box. And it depends on some number, integer n. There are many different possibilities, and we drew some of those, right? So if we have n equals 0, the wave looks like this. It goes to 0 at the edges, we know that, and then it's just one little hump. If n was 2, for example, no, this is n equal 1. N can never be 0. For n equals 2, it looks like this, where the edges again go to 0, and there's sort of a wave just like that. And you could just keep increasing that. But that's it. That's all it took to solve the particle in a box. And then earlier I said there are two parts to this, right? We needed to solve for the wave function, which we just did, and now we need to solve for the energy. But we know how to do the energy, right? We take the operator for the energy, and we operate on the wave function for it. So we did that. So it's minus h bar squared over 2m d squared dx squared times this wave function, right? And we ended up getting some energy times the same wave function, and we found that that energy I'm not going to go over the math again, but let me try to remember what that energy was. That energy was n squared h squared over 8ma squared. Right? You can do this math for yourself if you don't remember how to do it. I think we went over it last class, but it's also good practice. One other thing I want to add is notice here that there are many different possibilities depending on n. So we usually just put a little n here to say that the wave function depends on some number n. And that n could be 1, 2, 3, 4, and so on. So the wave function depends on some number n, and that's the wave function. Similarly, the energy depends on some number n, some integer n, and that's the energy. Any questions on that one so far? No. Okay. Let me know if you do. So I mentioned that this is a particle in a one-dimensional box, and you're thinking, well, nothing in the real world is one-dimensional. Actually, before we go to some applications, I just want to see if you can use this. Let's do that. Let's solve some problems with this. I want you to find the two lowest eigenvalues. You know what? I'll solve a big chunk for you. So this energy depends on some number n, and so the lowest energy would be when n is equal to 1, right? And the next lowest energy would be when n equals 2. We can just put n e2 and so on, right? Because n is on the numerator here. If you wanted to find the energy difference between, let's say, some final state and some initial state, kind of like that, then the energy difference, right, would be nf squared h squared over 8ma squared, right? That's the final energy minus the initial energy, kind of like that. But you could simplify this to just be h squared over 8ma squared, and then this nf squared minus ni squared. And that's energy difference between two levels of this particle in a box setup. So that will make my asking of this question, I'll simplify the question. So find the energy difference between the two lowest energies of a particle in a box with length, let's say 1 angstrom, which is about the size of an atom. That's 10 to the minus 10. So 1.0 by 10 to the minus 10 meters. So find the energy difference between those two lowest energy levels. If you have an answer and you would like, you can type it in chat. Pay attention to your units, right? we're gonna use, I actually didn't tell you what kind of particle it was. Let's use electron, because you need to figure out what mass to use, right? Let's use an electron. All right, I saw an answer. Gonna trust it because it seemed like the same correct order of magnitude. Um, so that's how we found it, right?
Hey, Dr. July,
Sorry, yep.
can you explain to me where the 2 and the 1 came from?
Wait, hang on, my volume is low. Sorry, go ahead.
Can you explain where the 2 and the 1 came from? I'm just a little confused. The ends.
Oh, so remember when we wrote this equation right here, right? The NF and the NI are the final and initial level of these integers n. I mentioned that the lowest energy would have n equals 1, the second lowest would have n equals 2, and so on. So if I wanted the difference between the two lowest levels, and the initial level will be n equals 1, and the final level will be n equals 2. You could have swapped those and your energy would be negative, which would have been fine too. But that's where the 1 and 2 came from. Does that make sense?
Yes, thank you.
Yeah. Yeah, it comes from the statement, the two lowest energy levels. All right, so 1.8 by 10 to the minus 17, that's a pretty decent amount of energy, right? I think that's in the visible region, maybe even in the UV region, I don't remember, but you can convert that to wavelength to check it out. But now, so this is a box that's 1 angstrom, about the size of a hydrogen atom, right? What if we made that box larger? So let's do the same. I don't want to write the whole thing again. Do the same for a box that is, let's do simple, 1.0 meters long. So more, no, sort of macroscopic level box. And let's look at that energy difference. So it's an electron, again, in a box that's 1 meter long.
Can you go through the unit cancellation real quick?
Yeah, okay, I'll do that right here. So on the top, we have 8 squared, that's units of joules times seconds squared. On the bottom, it's 8 times mass is 9.109 times 10 to the minus 31 kilograms. And the A is the length of the box, and it's 1.0 meters, but that's squared. And then this is 2 squared minus 1 squared. So joules, right, is the same as kilogram meters squared per second squared. So joules times seconds is kilograms times meter squared per 1 second, because one of the second cancels out, right? So if I square that, and so I wrote it like this, if I square that, I end up with kilograms squared, meters to the 4th power, right? Squared times square is 4th power, and per second squared. And on the bottom, right, if I take the this is so that's squared, meter squared, right? I just wrote it like that. So let's look at the cancellations now. One of the kilograms cancel out with one of the kilograms. The meter squared cancel out with two of the meter squares on top, which leaves us with just meter squared. So the units that we're left over with there is kilograms, meters squared per second squared, which we said earlier was joules.
Okay, thank you.
Mhm. So this answer, since all the numbers are similar, it should also be 1.8 times 10 to the something joules. What is that something?
Negative 37.
Negative 37. So let's consider that. If you have a box the size of an atom, right, the energy difference is large in the visible region. If you could see that easily, right? It's in the visible region. You could create instruments to see that. If the box is larger, macroscopic, the energy difference is so tiny. I don't even know if we have instruments to see that tiny energy difference, honestly. Maybe we do. I'm not an experimentalist, but I don't think we have instruments to see that tiny energy difference. But the point that I wanted to show here by working out these two problems is that when things are tiny, quantum effects are more pronounced, right? The energy difference was large and you could see it. But with the same quantum mechanics, when it's macroscopic, when it's larger, quantum effects are large. Quantum effects are negligible. I don't know how to spell negligible. I assume that's it. You get my point. So this comes back to the idea that it's not that quantum mechanics doesn't apply to large scale things like you and me and a car driving on a road. It does, but their effects, like the energy differences and all that, just is so tiny that it's not worth thinking about. That's it. So yeah. And here the other thing that I wanted to point out was we have quantization of energies. We have energy differences, not a continuous energy spectrum. And why did that come about? It came about because we had to force this wave function to go to 0 at the edges. If we didn't have to do that, we could have gotten any old energy from the system. But because we have to force the wave function to go to 0 at the edges, we got quantized states with different n values. Now you might all be thinking, well, it's a one-dimensional box. How useful is that really to do real world things? But I did mention last time, just before I left, that conjugated pi electrons are a very good use case for particle in a one-dimensional box. And I'm going to draw a molecule. I looked this one up this time so that I could draw a real molecule, beta carotene. Right? I think that's how it's spelled. So beta carotene, for those organic chemists in the crowd, I think looks like this. So we got a little ring there with a thing. And if you guys know what beta carotene looks like and this is not it, because I missed something, let me know. So that's beta carotene, right? Unless I'm wrong. So we have beta carotene, and the electrons in this conjugated pi system, right, moves back and forth along this chain. And it only moves back and forth in one dimension, back and forth. There's no, right? So particle in a box can be used to model the system. So let's say that the length of this box from this tip to that tip, let's say the length there is, I think it's, let me look it up. It's 2.4 nanometers. That's the length of the box. Now, here's the one other sort of point that I should mention. How many pi electrons are in this system, right? There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 pi electrons. And we know that any energy level could fit 2 electrons, right? We know this from Gen Chem. So that means that the first 11 energy levels are filled, right? So basically what I'm saying is n equals 1, that's filled. N equals 2, that's filled. N equals 3, that's filled. So if this system, beta carotene, was to absorb light, then it will go from n equals 11, which is the highest energy orbital that's already filled, to n equals 12. That's the transition that will happen if this thing absorbs light. What I want you to calculate is what is the wavelength between these two energy levels in beta carotene. So these are electrons we're talking about, right? So what is that wavelength between these two energy levels? For comparison, the wavelength from experimental study is around 450 nanometers, right? That's smack dab, I think, in the greenish area of the spectrum, which makes beta carotene look sort of reddish. So we're going to use this very simple tool that we just solved, even though it's for a simple one-dimensional system. We're going to see if we can apply it to beta carotene.
What's the mass of beta carotene?
It's the mass of an electron.
Oh, of an electron.
Yeah, these are all electrons that are moving. just as a reminder, once you got the, and once you have the energy, right, we need to use this relationship. The energy is h times the frequency, or the energy is h times c over lambda to calculate the wavelength. So we'll call this section application of 1D particle in a box, or subsection. The experimental value was 450 nanometers. It's probably not going to be close. Because we made a whole bunch of assumptions. Eight point, yeah, 8.2 by 10, okay, 8.25 by 10 to the minus 7 joules. And then we did wavelength would be hc over energy. So that's 6.626 by 10 to the minus 34 times speed of light divided by 8.25 by 10 to the minus 7. All of this would be meters. Oh, sorry. Thank you. Yeah, I thought that was weird. 2.40 by 10 to the minus 19 June. That makes more sense. 10 to the minus 19. All right. And 2.4, 10 to the minus 19. And it comes out to be 825 nanometers or so. Yeah. But so 825 nanometers, not quite the same as around 450 nanometers. But think of all the assumptions we made. We assume that this is a particle in a box where the potentials go to infinity outside the box. That's not true, right? Like for a realistic molecule, the potential doesn't just go to infinity. Secondly, we assume that it's just a one-dimensional box. Here, it's sort of a one-dimensional box, more or less, but the electrons have room to zigzag in the other dimensions. And then we didn't even talk about like particles interacting with each other at all. We just talk about one particle in a box, and that's what we model this. So the fact that we even got something that's a discrete energy, even though it's about twice what we got what's we got experimentally. Just from by setting up a particle as a wave, we have an explanation for what's happening in molecules, which you could have never gotten from classical physics, right? So the fact that we could even predict something that you could never predict with classical physics using this simplified version of quantum mechanics is pretty amazing. So that's one application of particle in box. We can use this to just sort of understand how pi conjugated systems behave. Another application for it is something that we call quantum dots, right? And if you basically what these are is if you take a piece of metal, we know that metals work, but because they have positive ions with C of D localized electrons, right? Those positive ions are pulling the electrons in. So it's kind of like a well, right? There's a well. I mean, it's not going to be a square well, but probably like that, where inside here is low potential where the energy gets pulled in, and outside is higher potential that the electrons don't want to escape. And so this looks like a one-dimensional particle in a box. And for quantum dots, right, you could actually calculate their levels based off of the size of those dots. So quantum dots are small pieces of metal, nanoparticles, of a few nanometers in size. And the larger they are, it corresponds to like a larger well, right? So you could use the same principles as particle in a box, where the length of the box changes based off of the size of the particle. So that's exactly sort of another application of this idea of particle in a box. Does that make sense, everyone? All right, I'm sure there's more applications, but these are the two that I think, well, I'm interested in quantum dots and nanoparticles, and I'm sure everybody has done pi conjugated systems in organic chemistry.
So can quantum dots then also absorb light?
Yeah,
and
quantum dots absorb light.
fluoresce
Do they fluoresce?
or re-release the light?
They do. Yep, that's exactly how they work. And you could create them to absorb any color of light that you want just based off of their size, right? You can like, the larger it is, the lower energy wavelength it absorbs. The smaller it is, the higher energy wavelength it absorbs. But yeah, you can design them to absorb any sort of light. All right, so that brings us to the end of the particle in a box. Again, I will always give you these equations on sheets, equation sheets for exams, but let's write it this way, n pi x over a. That's the wave function for a particle in a box, and that's the energy for a particle in a box. So you don't necessarily need to remember it, but you need to use it and recognize it when you can. Any questions on those? All right, so we went all the way from saying particles should be described by wave functions all the way through to actually solving for one of those wave functions, right? But all the way back in the beginning, I mentioned to you everything that we wanted to know about a particle is in that wave function. And we sort of set that up by looking at operators and eigenvalues and all that good stuff, and say that the only things that we can observe come from eigenvalue equations. But what else can we get out of the wave function, right? What else, what other kind of information is contained in the wave function? So that sets up a section that I'm going to call properties of wave functions. And in this bit, what we're going to look at is we're going to describe nodes and probability density. Of wave functions. We're going to calculate average or expectation, as it's called, values of observables. We're going to calculate uncertainty. This one is actually not in your textbook, but I think it's important. We're going to calculate the uncertainty of an observable. We're going to describe orthogonality relationships. Some of these might sound like weird things unless you've read ahead, which is, is great. And then we'll understand finally the process of quantum tunneling, which I already did some animations for in your third Jupyter notebook, even though we probably even won't get to it by the end of this week. We'll see. So those are some properties of the wave function that we're going to look at. And the reason why we sort of put this after we solve the particle in the box is, for most cases, we're just going to look at the particle in the box example case to find each of these properties. So let's start with probability density. So let's look at probability density and nodes. All right. So earlier in the semester, we talked about how the probability of a particle between 2 points, A and B, is this equation here, psi star psi d tau. Tau just means integrate over all space, right? So if we were to draw a graph, right, of the wave function, let's say, I don't know, this is the wave function. Psi star psi is the square of that wave function, right? So if you square a positive number, you get a bigger positive number. You square a negative number, you get a positive number. So it might look like that. So this would be psi star psi, whereas the green would just be psi. And we said that the probability would be kind of like integrating under, let's say this is point A and that's point B, would be like integrating under that curve. Right, that's what integration is. You find the area under the curve, right? So this quantity here is actually very useful. That quantity there, people usually write it this way, psi star psi, inside of these, I don't know what you call those, little absolute value brackets. I don't know what you call them. That is what we call the probability density. You integrate that to get the probability. But by looking at the probability, its density itself, we can tell a lot about a system. For example, let's look at the particle in the box wave functions. Like I said, we're going to do that for a few cases. So let's set up, I'm just going to draw a few boxes. And this will be the n equals 1 case, n equals 2 case, and n equals 3 case, right? And in n equals 1, the wave function kind of looks like that. And n equals 2, the wave function kind of looks like that. And n equals 3, it looks like that. And it gets harder and harder to draw, so I'm just going to stop there. Right, so that's psi. The green ones are going to be psi. The probability density is psi star psi. What that means, psi star psi, is, remember, it's the complex conjugate times the complex conjugate times the wave function, which means that the imaginary parts are actually going to cancel out. So this, whatever is in this here, is going to be real. The square modulus kind of lets us know that it's also going to be positive. It's never going to be negative, right? So anytime you see a negative value, you make it positive. Anytime you see a positive number, it's squared. So psi star psi, the probability density for the first one looks like that. It's just taller. Here, that one's taller, and the negative part becomes positive when you square it. Here, similar thing, positive gets taller, negative becomes positive and taller, and positive gets taller. So those are all the probability density psi star psi. What does it mean, the probability density? Well, it means if you integrate a small area, very, very tiny area here, right? The height of this will give you that probability. More or less, right? So the height of this psi star psi, and I just accidentally erased that one, gives you an indication of the probability of the electron in a very tiny spot, dx. Let's say you have a very tiny sliver we can call dx. The area there gives you sort of the probability in that small area, right? So you can think of the height of this curve as some representation of the probability of the electron. Does that all make sense? Now, I want to point out some very important area. Well, one very important area to you, which is right here. The wave function, the green line, crosses the x-axis and goes from positive to negative, which means that the probability density here goes to 0. Right? Like 0 squared is 0. So the probability density is 0. Here, the probability density is also 0 at those 2 points. These points where the probability density goes to 0 are called nodes. So for a definition, a node occurs whenever psi star psi, or you could write this like this. It's actually a faster way to write it. Just psi squared within the square brackets goes to 0. So up here, you can write psi star psi or just psi square. They're essentially the same thing. And this is actually shorter. So that's it. That's a probability density and that's a node. So basically at a node, you have 0 probability of finding an electron. It's kind of a weird concept. You're saying that a particle is in this box, somewhere in this box, but there are points in this box where the particle never goes. But somehow the particle jumps between the different positions without ever going exactly at where the nodes are. Does it disappear here and appear over here? I don't know. But again, we don't want to interpret what the wave function means. We're just trying to understand properties from it. One of those properties is that there are spots called nodes where there's 0 chance of finding electron.
If we look back at the beta carotene example, are those nodes located at any particular spot on beta carotene, I guess?
This one, it's not easy to know.
Okay.
Actually, yes, there are lots of nodes in beta carotene, but not analogous to what we can learn from particle in a box.
Okay.
But since you brought that up, we're gonna do this later in the semester where we're gonna actually solve for like a real atom. But let's look at remember s orbitals look like spheres and p orbitals look like dumbbells. Do you guys remember this from like Gen Chem? All right, right in the middle there, that's a node. Because the p orbitals, one side of the lobe is like positive for the wave function, and the other side is, negative for the wave function. So right in the middle there where they cross over becomes a node. So whenever you see those like orbital shapes and the sign changes between one part to another, right in the middle is where a node would be. But we'll get there. We'll get there in a bit. So yeah, beta carotene has lots of nodes in its wave function, but not for the pi conjugated electrons necessarily. All right, so we learned about the probability density, we learned about nodes. Let's look at average values. Sometimes they call this the expectation value. Why expectation? Because if you solve this infinite number of times, the average value that you expect, actually, I don't know why they call it expectation. The average value that you could expect from such measurements is what we're about to calculate. Okay, so earlier we talked about how observables have operators, and the only observables you can have are those that set up eigenvalue equations, right? If you do not have an eigenvalue equation, you can't observe that value. We mentioned this. But what that means is you cannot observe that value at any one instant, right? But you can still make measurements on systems. The problem is we just can't figure out what answer you'll get when you make that measurement. But what we can figure out, so this, how do I say this? This lets you make an instantaneous measurement of an observable. Right? If you don't have an eigenvalue equation, you can't get an instantaneous measurement. For example, let's say you have a particle with some wave function, but the position operator, right, is not an doesn't set up an eigenvalue equation. It means that you can never instantaneously measure the position of the particle at various points in time. But what you can do is measure positions over and over again. Each time you might get a random answer, right? But over time, you can come up with an average value. So over long times, or after multiple measurements, we can get an average value of an observable. Let me show you what I mean, but just by looking again at a particle in a box, because it really sort of helps us. So this is the n equals 2 level. That's the wave function, right? And this is going to be the probability density, psi squared.
Can you go back up for a sec? Sorry.
Oh.
Or back to the, thank you.
All right, so let's look at this little system to the right that I drew. Right, particle in a box, we have the wave function, we have the probability density, psi squared. If I were to ask you where in that box is the particle, what would your answer be? So it is sort of a rhetorical question, because we don't know what the answer is. Why? Because we already solved this, I think, earlier. But we know that if we use the x operator on a particle in a box wave function, we don't get a constant times the wave function back, right? We tried this and it doesn't work. So basically what that tells us is, if we were to ask the question, where is the particle? The answer is, I don't know. You can never find it. We do know that there's a node right here. So we know for sure that the particle is not there. But that's not a good enough answer, right? We know where the particle is not. We don't know where it is. I know if this is not boggling your mind in a second or right now, I don't know what will, but we don't know where the particle is because we can't solve an eigenvalue problem with the position operator x hat. We do know probabilities of finding the particle. So there's some probability of finding the particle here, and that probability is larger than finding it here, or here, or, you know. So there's probabilities of finding the particle, but we don't actually know where the particle is. What we can get, though, is some sort of average value if you were to measure this particle position over long periods of time. So for example, if you were to measure the particle at some point in time, you might find it over here, this point, because there's a higher probability here. But if you measure it at a different time, you might find it's over there. I mean, there's some probability of finding it there. You'll never find it in the middle here, that's the node. But you might find it over here. Like every time you make a measurement, you might get a different answer, is what I'm trying to say. Does that make sense? Because you don't know where it is, you just have probabilities. But what the average value is able to tell us is what happens if you make measurements over and over and over and over again. What's the average of all the answers that you're going to possibly get? And the way we set that up is using this. So this is the, I'll write it generally for any observable O. So this is some average value of observable O. And that you can actually find using this equation. You integrate over all space over psi star, the operator for that observable, psi d tau. So this here is the operator, and that is all space. So if it's x, it's just x. If it's x and y, it's x and y. Yeah. And the other thing that I want to point out, for this to work, psi must be normalized. This statement right here becomes the fifth quantum mechanical postulate. So quantum mechanical postulate number 5, the average or expectation value of an observable can be found with this equation. So even if the observable does not set up an eigenvalue problem, you can still find an average value for it. If the operator does set up an eigenvalue problem, you can still use this to find the average value. And I just want to add this caveat. If up here we said psi must be normalized, if psi is not normalized, we can use this equation here where the average value becomes the integral over all space of psi star the operator psi d tau divided by just the normalization integral, the integral of the probability density, like that. In case you don't have a normalized wave function. It might just be easier to normalize it first, then use that equation. But either way, it's the same amount of effort. If the wave function is normalized, this part on the bottom goes to 1, right?
Can you scroll up some?
Sure.
Thank you.
Can you still read all that so tiny? Okay. So far we've been doing a lot of differentiations of various things. Very little integrations. But now that we've introduced this idea of expectation values, oh, we've done integrations for probabilities. Okay. I was just thinking whether we've done it or not. All that is to say though, you should start flexing your integration muscles because we're going to do some problems that involve integration.
So could we do this for the particle in a box then? Like
Yeah.
this process, but for position then?
Mm-hmm. So let's do that. Does everybody have any questions? Or shall we do some practical examples? All right. So let's do some practical examples. And again, I don't like to rush things at the end of sessions, but let's prove to you that you can't find the instantaneous position from this equation. We talked about it, but let's do it. Let's find the instantaneous position of a particle in a box. I'll just call it PIAB with n equals 2. So that equation would be root n equals 2 and a equals 1, just to make this all easy. So this would be square root of 2 times sine of 2 pi x. The position operator, we know, is x hat, which is the same as x multiplied by something. And psi is normalized, in case you're wondering, between 0 and 1. So that's the length of the box. It goes between 0 and 1. So let's try to find the instantaneous position of this particle in the box setup. I'm going to work it for you, right? We know that the operator times the wave function should give us a constant times the wave function. The operator is x multiplied by the wave function is square root of 2 times sine times 2 pi x. But there's no math to do here. This is not a constant, which means we can't find position. That's it. Right? So hopefully I just proved to you that you can't find the position of a particle in a box at any time, any instantaneous position. But now let's find the average position of the same particle. The same particle in the same box, so that I don't have to write back all those things again. Let's try to find the average position. And I'm going to work this out. We only have 6 minutes, so I'm going to work this one out. And then when we come back, I'll refresh it and then give you one for practice. So I mentioned that the average value, we put it in these little angled brackets. It's going to be the integral over all space of this wave function star times the operator times the other wave function over all space, right? In this case, the integral goes between 0 and 1 because that's the box that I mentioned between 0 and 1. So that's what we'll do. Integral between 0 and 1. The wave function was the square root of 2 times psi of 2 pi x. The x operator is just x multiplied by whatever comes after it. And then we have the wave function again, square root of 2 times sine of 2 pi x dx. Everybody with me on this one? Okay, so let's simplify this. Square root of 2 times square root of 2 is just 2. And we can take that outside. The integral goes between 0 and 1. Sine 2 pi x times sine 2 pi x becomes sine squared 2 pi x. And then there's x right there. So it's x times sine squared 2 pi x dx. At this point, you would just look this integral up in your integral sheet, right? So once you look this up, you'll find that the integral is actually, so we rewrite the 2, and this comes out to be x squared over 4 minus x over 8 pi times sine of 4 pi, if I did this math correctly, 4 pi x minus 1 over 32 pi squared times cosine of 4 pi x. This goes between x equals 0 and x equals 1. Let me just pull up a equation sheet just to see whether this is correct or not. So an equation sheet that I gave you would have this in all exams. You would never have to like remember this. So if you're seeing my screen, I'm using x times sine squared bx. So I'm using this integral here, this identity, right? And it's x squared over 4 minus x over 4b times sine 2bx minus that identity, right? And in my case, b was just 2 pi. So I made that substitution. Does that make sense, everyone?
Is that 3 pi squared there? Should that be something different?
Yes, that should be something different. It's 32 pi squared, sorry. 32 pi squared. So I would write, again, you don't need to know how to do these integrals. Not a math course. You just need to read the integrals that I give you and translate that to the page, right? But now that we have this integral, we just solve for the limits, right? So 2 is multiplying everything. So let's just keep 2 times everything. And we'll solve for the x equals 1 limit first. So if x equals 1, x squared is just 1. X is 1, so that's 1 over 8 pi. X is 1, so it's sine of 4 pi, right? And then minus 1 over 32 pi squared times cosine of 4 pi. All right, so that's the x equal 1 limit, and then we're subtracting x equals 0 limit. 0 over 4 is 0. 0 over 8 pi becomes 0. So this whole thing is 0. And then minus 1 over 32 pi squared times cosine of 4 times pi times 0 is 0. Does that make sense, everyone? I would challenge you, if this is a little bit too fast, to do these by yourselves to see if you get the same answers. But now let's simplify. So 2 is multiplying everything. That's 1 over 4. Sine of 4 pi. Sine of any integer times pi we mentioned is 0, right? 1 pi, 2 pi, 3 pi, 4 pi, they're all 0. So this part goes to 0. Cosine of 4 pi is 1, right? This is 0, that's 0. Cosine of 0 is also 1. So I end up with 1 over 4 from here, minus 0, that part's 0, minus 1 over 32 pi squared, right, times 1. Here's minus 0, 0. Minus and minus becomes a positive here, right? Minus minus is positive. So this is plus 1 over 32 pi squared times 1. And here we just see that we have a positive that, negative that, it cancels itself out. So we have basically 2 times a quarter, which is just a half. Now that answer I don't know if it freaks you out or it makes logical sense, but let's examine the system that we looked at, right? We examined this system here with n equals 2. We said we can't find the position. We said that there's a node in the middle, which means the particle can never be in the middle. This box goes from 0 to 1, right? But the average value of the particle is exactly halfway there. That is, the average value comes out to be halfway. It should make logical sense. It means that half the time the particle is on the left side of that node, half the time it's on the right side of that node. So on average, you can say that the position is exactly in the middle of the box. Does that make sense? Or if it doesn't make sense, that's fine too. But the logic here is the particle is never in the middle, but on average, if you keep measuring numbers, right? Sometimes it'll be over here a quarter, sometimes it'll be over here 3/4, and so on and so forth. Until if you measure this infinitely many number of times, you'll get an average of exactly in the middle of the box. Any questions on that? No, I see some puzzled faces. So I'll leave you there. I'll leave you to think about that for a second. So even if you can't find eigenvalues for operators, you can always find average values of operators, and their answers can sometimes surprise you. And to do that, to find their average value, we need to always do this integral. If you're finding the instantaneous expectation value from eigenvalue equations, this is what you solve, an eigenvalue equation. But if you're finding the average value, it becomes an integral. I'll leave you there. If you have any questions, let me know. Otherwise, we'll see you on Wednesday. We'll go over this and yeah, we'll go over this. Any questions you have?